Let's solve one more problem related to, let's say, cell tripling time. I think this is something we solved already. But here we have some different type of data. So let's say we performed a microbial reaction using some bacteria. Follow the red color pen using some bacteria. So this time we are monitoring the microbial density using a turbidity meter, and then we obtain the following data. So earlier we solved some problem. So in that case I gave you the monod kinetic constants. From the monod kinetic constant you solved you obtained the specific growth rate, and from the specific growth rate you calculated the the doubling time or tripling time, whatever. Yeah. And now we have time versus cell mass, and from with this type of data you need to calculate the cell doubling time, or we can call the cell generation time. Okay. Okay, not even doubling time, we are going to calculate maybe we can call it like a tripling time, because we are going to assume at each cell division a cell produced three daughters. Okay. So how to do this? So we have cell mass, so let's say x grams per liter. So that's the notation we always use to represent the microbial density or concentration. And to calculate the cell tripling time, we need to follow the same rule. Let's assume the microbial growth follows the simple first order expression ln of x by x0. And what we have here is, if we start our experiment with x0, that's our initial concentration, initial microbial concentration, then after the first cell division x will be equal to 3 times x0. So which mean ln of 3x0 by x0 will be equal to mu multiplied by the T cell generation time. So we need to calculate specific growth rate. So how to get this value? How to get this value? It's not difficult. So let's fix the page number first. So we are in page number 8. Okay, let's calculate the cell generation time. The cell generation time is okay, we have the expression x0 get cancelled, so T generation will be equal to ln of 3 divided by mu, which is your specific growth rate. So we need to get this mu value from the data which we have here. And if you assume that the growth of microorganisms follow the simple rule ln of x by x0 is equal to mu t, then we can use this expression to calculate the specific growth rate, which is your mu. So to do that, all we need to do is we have to plot ln of x by x0 versus time. You will get some line like this from the slope. That slope value should be equal to mu, and this trend line should pass through your origin. So why is that? That's because this is a linear expression. So page number 9. So ln of x by x0 equal to mu t. So this is a simple linear expression. Same, y is equal to mx plus c. In this case, your c value is equal to 0. So which means if you plot x versus y, you will get a line, and that intercept will pass through 0 comma 0. That's why c is equal to 0, and your slope value will be obviously equal to m. And in this case your y value is equal to ln of x by x0. X is equal to your time here, and your slope value will equal to m here, and your intercept value will be equal to plus 0 here. Yeah. So that's the idea behind this. So we need to we have time here. Time is expressed in minutes, I believe. Time is expressed in minutes, and we have our microbial concentration. So I'm going to calculate x by x0. So what is this x0? If you go back to the table. So x0 is your initial microbial concentration. So when time t equal to 0, whatever the microbial concentration that you have, that's nothing but your initial microbial concentration, that's nothing but equal to your x0 in this expression. So your x0 will be equal to 0.1 grams per liter. So we have time 0 0.51, 1.5 and then 2. So we have to calculate ln of x by x0, that's nothing but ln of 0.1 by 0.1, ln of 0.15 by 0.1, natural log of 0.23 by 0.1, natural log of 0.34 by 0.1. Sorry for going a bit slow, but it's okay to do this way. So what this value, this will be equal to this will be equal to 0, ln of 1 is 0, and then let me calculate it. So 0.41, this will be equal to 0.83, this will be equal to 1.22 and then 1.63. So we are going to plot. So we have time, we have ln of x by x0, so we need to plot time versus ln of x by x0. Yeah? So time is expressed in terms of minutes. So this is dimensionless, x by x0, that's because grams per liter, which is x, grams per liter, both gets cancelled. So no units on the y-axis. So let's plot it. At the moment I am using a normal simple scale. You have to use a graph sheet. So how to do that? So let's plot say 1 to 2, and then again 1 to let's plot it here. So I'm not using a graph paper, that's why I'm taking extra bit of time. Say 0.5, 1, 1.5, 2, and let's say here 1 and then 2. So we are going to plot x 0 comma 0, that will be around here. Next value is 0.5, that's equal to 0.4, so roughly around here. And then 0.83, that's equal to 1.22, 0.83. That's roughly around here. And then 1.22, that's equal to, oh sorry, I think I did a mistake. So 0.5 is 0.41, and then 1 is equal to, ignore this point, 1 is equal to 0.83, so that's somewhere around here. And then 1.5 is equal to 1.22, somewhere around here. And then again, when x time t equal to t2, ln of x by x0 is equal to 1.63, that's somewhere around here. So all we need to do is draw a line that should cut through the origin. Oops, that's not a line. So all you need to calculate is the slope value, so that should give some rough idea about your specific growth rate. So let's calculate that. So this should be equal to 0.5 and then 1, that that should be equal to 1. And what we have here in this slope value, so that's roughly around 1.5. See, roughly it's 0.6 maybe. No. Okay, this is roughly around 0.5, 0.7, 0.8. It's around roughly 0.8. So your slope value will be around 0.8. So that's nothing but equal to your specific growth rate 0.8. And what's the unit? So we expressed x in terms of grams per liter and time in terms of minutes. So your mu value will be 1 by time unit, so 1 by minute. So that's the unit of your specific growth rate. Mu is equal to 0.8. So this is something you have to calculate. So we have your mu value. So now we can calculate the time, cell generation time for the condition that after each cell division a cell produced 3 daughters. For this condition we need to calculate the cell generation time. So which means T generation will be equal to this expression. Just follow the pen. So T generation will be equal to ln of 3 divided by specific growth rate. So that will be equal to ln of 3 divided by 0.8. That should be equal to ln of 3 divided by 0.8. That should be equal to 1.37 minutes. So pay attention to the units. If a time is expressed in minutes, obviously TG is going to be in minutes. So this is enough for the moment, and then we will solve some more problem where we are going to use that the bit complex expression, Edwards expression. Okay, so this is enough for the moment. I will stop now.